how they are and how they come up later if some of you are interested. But can you note something about them? Can somebody make one observation about what is common to both of them? In what sense? So yes, that one is, yes, of course you can draw an axis and you can reflect. Yes, there is symmetry, but there is much more than that. Right? So what I want to point out is that each of them is made up of several copies of scaled versions of itself. Okay, so if you see this picture on the right side as a whole, and if you zoom onto a part of it, it's again a copy of the whole. You see, like this whole figure is like kept in different scaled versions. I mean, are kept along the boundary. And if you zoom in on that boundary, also there are scaled versions of it. Okay, and the same is true for the picture on the left. Okay, but that's agreed, everybody? Yes, but that's not the thing that is common to both of them. There's something much more common to both of them. Okay, so we'll come to that towards the end. Okay, at the end, this will be the test of whether you're interested in these figures or not. Okay, so let's move ahead. So I gave this slightly cheesy title, Unexplored Dimensions, right? So of course, I want to talk about dimensions. What is dimension? Right? Dimension is a number that we associate to what we see, right? We say that if you see a point, it's of dimension 0, things like that. Okay. So it's our mental picture. When we see a figure, we associate a number to it. Like a point has dimension 0, a line has dimension 1, a plane, that means like the surface of the screen is of dimension 2. And then the world that we live in is dimension 3, it's 3D, right? So I want to discuss what is this D? What is this dimension? Okay, and 0, 1, 2, 3, 4, and so on, are these the only dimensions? So what is dimension? This is the question that I want to address in this. Okay, so one very, very crude observation that we can make is that the dimension of a number tells us something about how it fills space. Okay, so now we live in a three-dimensional world. So we know how three dimensions look like. So if you take a two-dimensional figure, let's say a sheet, you will require tons and tons of them to fill it up, right? But if you are given a cube, then you can see that maybe just finitely many will do. Okay, you can take many copies of it and you will be able to fill it. And the same is the relationship between 2 and 1 and 1 and 0, right? You can't just take finitely many 100 points, 1,000 points, 10,000 points and make a line. You really need infinitely many and many infinitely many in a particular manner. Okay, you can't keep 1 meter away from each other and then hope to get a line. Right? You need them very close and you need infinitely many, uncountable. Okay, so it gives us an idea about how to fill space, but that's a very crude one. Okay, so how do we assign these numbers? Okay, so I'll take you back 100 years ago. I'll take you back to a mathematician who first tried to make an attempt of how to go about defining dimension. Okay, so we declare that a point has dimensions. Okay, and we say that if you are given like a finitely many collection of points, 10 points, 17 points, 3063 points, they will all have dimensions here. Okay, and a line or a curve has dimension 1. Now, how do we relate these two concepts? So, here is a very crude observation. You take a line and you remove some point out of it, then you can disconnect it. Right? So, you take this line curve on the left, you remove any point, you will make two pieces. You will break it up into two pieces. Now, if you remove any one point on the curve on the right, you are not going to break it into two pieces. Okay? Removing one point does not do it. But if you remove one, how many? Can you tell me how many points should be removed to disconnect this, to make two pieces out of it? Okay, so 3 in the middle for sure, and then one on each of the arms. If you remove those, then you will disconnect it. Okay, 4 will also do, I guess, if you choose them very carefully. Okay, so, but the point is that if you can remove finitely many points from a curve, and suppose you can disconnect it. Okay, you are given an object, you can remove finitely many points and you can disconnect it, then we will say that it has dimension. Okay, this doesn't work for a surface, right? A surface is like a sheet. Okay, can you disconnect it by just making holes into it? No, right? What you need to do is you need to take a scissor and cut it through. So you need to remove a curve to disconnect it. Okay, so this, I mean, this is the main point, right? You can't disconnect it by just punching holes in it, but you can disconnect it by removing a curve, by cutting over a curve. Okay, you see the difference? So you can, similarly, it's true for the 3-dimensional space. I'm giving you this cube. It's okay, you need to remove it or, yeah, that's better. So suppose I take this table and I want to, this is a 3-dimensional object. I want to disconnect it. I cannot punch holes in it and disconnect, or I cannot like draw lines with a cutter on it and disconnect. I have to really remove a sheet, like remove, I have to take an axe and break it into two. Okay, then I can break it. Okay, that's the idea. So similarly, you can go by this very simple idea that an object is n-dimensional if it can be broken into at least 2 parts by removing an n-1 dimensional thing into it. I have, so this process is called induction. Okay, so this definition has a problem. I'm going to come to that. So this process is called induction in mathematics. You check, you assume something that is 0-dimensional, then using that, you define what 1-dimensional is. Then using that, you define what 2-dimensional is, and then you go on and on and on. Okay, so this definition has a problem. Okay, now I'm giving you a surface. Okay, like this. So they're like these 2 inverted tops joined to each other. Okay, now this can be disconnected by removing a point. Yeah, so this point of contact, if I remove, I will disconnect it. So, you know, this idea, which looked very natural and nice, it's not really perfect. Okay, so of course, mathematicians are mathematicians, pure mathematicians. What they try to do is that they try to get a watertight theory. Okay, I want to get a correct theory of dimension. That means I want to give a proper definition which will apply everything. And somebody did this a few years ago. So, how to fix this issue? So, how did this person fix this issue? Okay, so the name of this person is Pavel Urizov. Okay, he was a Russian mathematician. And as you can see, he did not live very long, only 26 years. Okay, this is the problem that he decided to work on during his PhD. I will determine the correct notion of dimension. And he did some very many fundamental contributions to an area of mathematics called topology. You might not have heard about it so far, but you can look at it. And then he gave an inductive definition of dimension. That means depending upon how to define n-dimensional object, it tells you how to define an n+1 dimension. He gave the correct definition. So he said the following, right? An object has dimension 0 if I want to look at any point of that figure that you have, and I want to look at balls of some small radius. That means some neighborhood of some small radius around it. And if that neighborhood has no other point of the figure, then I will call it dimension 0. You see, this I'm showing you a collection of points, and it is supposed to have dimension 0, right? So you can look at circles of various radius around a given point. Okay, if I take a circle of very big radius, it will contain all the points. But if I can look at a circle of small enough radius, then it will always avoid other points. Okay, is this idea clear? And if you can do it for every point, then yes, you have something of dimension 0. What will be the problem if you have dimension 1? There will be points very, very close to this point, right? There will be a line. That means there will be points close to this point. So no matter how small radius you take, this ball will always contain some other points of the figure. So one dimensional object will not come under this kind of a definition. Okay, so this process of looking at smaller and smaller things, coming closer and closer to things, is the first way in calculus and analysis. This is the notion of limits, which you may or may not have seen in your curriculum, or you might be seeing. Okay, so he did the same thing. You can repeat the same dimension for a curve, and so if you have a curve, then what happens is that if you take any point on it, and if you take a small enough neighborhood of it, then if you look at how many points of the curve are there on the boundary, it's 2. Okay. Similarly, look at a surface. Suppose you have a sheet. Okay. Suppose you have a bed sheet or something and you have a point on it. You take a small ball around it. What would be the intersection of the boundary? It will be some curve. Okay. So then you can have this idea that an object has dimension 2 if the following holds. Given any point of the object, you can find balls of arbitrary small radius around it, such that the boundary intersects in one less dimension. So anyway, the technicalities, words are not very important. The idea is that this is how you fix the issue. Okay, and this is what he did. And so you can proceed and you can define something that is n dimension. Anyway, I want to come to a very interesting figure. But before that, I want to talk a little bit about Pavel-Uvisson. So, it's really pure mathematicians are known to be crazy, right? Do you know how he passed at the age of 26? He was a very brilliant mathematician, and he was, of course, at such young ages, at such a young age, he was invited to international conferences. He was invited to a conference in Marseille, in France. Okay, so he had gone there, and there was a storm warning. He ignored that and went to swim in the sea. And then he drowned and died, unfortunately. So, yes, it's a really sad end to a great mathematician. But I mean, it's incredible because when I studied pure mathematics, in my topology course, many of the basic results were theorems of Urizon. So I was really amazed to see how, somebody can do everything like so much at such a young age. And yeah, it's really a pity. So moral of the story, don't be crazy, even if you are a great researcher. Okay, but now I want to come to another figure. Okay, I want to show you a figure, and I want to ask you what it is dimension. We know how to define dimension, right? We have seen this definition, but now I want to. Can you tell me how this figure is formed? And can you tell me what this figure is called? You might have seen this. This has become very, very popular lately. This is called the Sierpinski triangle. Because, of course, it's named after this Polish mathematician, Wacław Sierpinski. And so you can see the timeline. It's roughly post-Urizon. Urizon was already dead in 1924. And then people started noticing some other things, what to do with this. Okay, so does anyone know how to construct this figure or how to come up with this figure? Okay, so let me tell you. Okay, so the question is its dimension 2? Okay, and I'll give you a procedure how it is formed. So you take an equilateral triangle, you take a triangle with 3 sides the same, and then you look at the midpoints of all the 3 sides, you join them. Okay, and then you get 4 small triangles. You cut the middle triangle and throw it out. Okay, so I had a blue equilateral triangle. I made 4 small triangles out of it by joining midpoints, and then I threw away the middle one. Okay. Now I do the same thing because I have 4 small triangles, and then I take midpoints of the smaller sides, and again do the same procedure. Okay. Then I do this. Then I do this. Okay. So after every iteration, you get a 2-dimensional piece, right? Yeah. You had a triangle which was 2-dimensional. and then you cut up a piece out of it, then you cut up more pieces. Okay. Now I'm telling you what happens after infinite iterations. Okay. So if it's dimension 2, will it remain 2? How many of you think so? Yes? Okay. And others don't think that it is 2. So what do you think it is then? It will not go higher. So is it 1? 2, 1 or no answer or something else? None of the above. Okay? Okay, let me show you one more procedure. It's a nice question. Start with the line segment of unit length and do the following. Divide it in 3 parts. And so like each of the smaller ones, so each smaller segment is 1/3 the size of that segment. But I will take how many of them? 1, 2, 3, 4, 5, 6, 7, 8, 9 of them. Okay, not 1/3, sorry, 1/4. So this line segment, if you see, right, that would be half the line segment. So each line segment is divided into 4 parts. I have taken 9 pieces of that, 1/4 of that segment, and I have made this shape out of it. Okay, now you get the picture, right? What am I going to do? I'm going to remove, I'm going to replace each of those small 9 line segments. I'm going to take 1/4 of that, and I'm going to take this weird picture and I'm going to fit it in. Okay, so this is what happens after one iteration. Okay, what will happen after one more iteration? So the dimension is 1, right? This is what happens after one more iteration. And this is what happens after one more iteration. So at each stage, the dimension is 1, right? What happens if I do it infinitely many times? Okay. So the question is the dimension 1? How many of you think that the dimension is 1? Okay, yes. कुछ तो दाल निकाला है. There is something more to this. Okay. Okay, so let's see. Let's go back to, let's take a look back at the definition of dimension. Okay, so there is, so yeah, how do we determine dimension? I gave you one way, which is topological. Topological means it only looks at the shape. It does not take length, area, volume, these kind of measurements into mind. Okay, I want to now take another look at dimension. Okay, so our traditional notions of geometry tell us, dictate that shapes scale according to dimension. What does that mean? Okay, so if I take a line segment of length 1, or I take a unit square, or I take a unit cube, if I make 2 equal parts of the line segment, how many parts of the square I get? How many parts of the cube I get? Okay, so if I make 2 parts, I get 4 small squares and 8 small cubes. Similarly, if I make 3 small parts, then I get 9 squares and 27 cubes. So roughly what is happening is that you take such nice objects, and suppose n is the number of smaller copies formed because of scaling and r is the scaling factor, then d is the dimension. What should be the relation? Anybody? Yes? Yes, yes, but in terms of n, r and d? Kind of, yes, you're right. Okay, so you all know how to solve this, right? You take log on both sides, and then log of r to the power d becomes d times log r. So then you get d as log n divided by log r. Okay. Now somebody will ask, you are taking log, what base? Doesn't matter. Okay, you take whatever base, it doesn't matter. Exercise. Okay. So now what will happen? Okay, this gives us a new way to define the defined dimension, right? So the point is that there's nothing wrong with Eurizon's definition of dimension, but it's not the only dimension. You know, you remember I called it topological dimension. This is actually another notion of dimension. It's called the box counting dimension for the obvious name, because it's gotten by counting boxes. There is a technical term for it also. It's called the Minkowski-Boolean dimension. You can look it up. Now, I want to ask you, what is the dimension of a Sierpinski triangle? Okay, so you take, after every iteration, the triangle gets divided into 3 equal parts of exactly half the size. So for n equal to 3 and r equal to 2, the dimension is log 3 by log 2. Okay, and this, with respect to whatever base you take, the answer will be 1.58. Something. Okay, so now the question is, I calculated right like this. What if I calculate it the other way? Right, I took one segment, made 4 parts of it, took 9 of them. The answer will be log 9 by log 4, which is the same as log 3 by log 2. It's the same dimension, it's the same object. Okay, so there is no problem. So what is dimension? So dimension is not an absolute concept, and the dimension theory assigns a number to each object that we come across, and so these are the things that are supposed to be taken into consideration by assigning this number. And there are different notions of dimensions. I talked about topological dimension and the box counting dimension. There is something called Hausdorff dimension. I'm not going to talk about it. Hausdorff was a great German mathematician, who also has a sad story, unfortunately, because he could not exit Germany at the time of Second World War. But anyway, so I want to talk about fractals. So all of you told me what fractals. I mean, these were fractals, right? So what are fractals? So of course, fractals. The name has come from the word fractus, which means fracture. So as we saw the previous figures, these are geometric shapes that can be split into parts, each of which is a reduced size copy of the whole. And of course, these things were thought of a long time back in the 19th century, but the term was coined by Benoit Mandelbrot in 1975. And so they also have fractional dimension. Of course, there is an actual definition, but I'll not get into it at this point. But I, at this point, want to show you a small movie about how Mandelbrot noticed that there exist fractals in nature. And there is this big documentary which is available on YouTube. You can look at it later. Can you hear this?
Mandelbrot's colleagues told the young mathematician about a problem of great concern to the company. IBM engineers were transmitting computer data over phone lines, but sometimes the information was not getting through.
This is 1950s.
They realized that every so often the lines became extremely noisy. There was a very large numbers. It was indeed an extremely messy situation.
Mandelbrot graphed the noise data, and what he saw surprised him. Regardless of the time scale, the graph looked similar. 1 day, 1 hour, 1 second. It didn't matter. It looked about the same.
Okay, so this is what he observed. He just graphed, there was a lot of noise. They were trying to transmit signals. There was a lot of noise that was coming, and he just tried to analyze it. And he just took readings over lots of time intervals. And he saw that the structure of the pattern was exactly the same. Okay, so this is why he thought of things that are rescaled versions of themselves, and which at arbitrarily small scales look exactly the same as 4. Okay, so now I should place the cursor. Why can't I go? What happened? Where did my slide go? Yeah. Okay, so I think we'll have to stop at 5 o'clock, right? Yeah, but they will tell, right? There'll be an announcement. Okay. So I want to, so after this thing, I want to look at another example of fractals, and that's the coastline paradox. Okay, so suppose that we have to measure the length of the coastline of a country. Okay, so let's try to measure the coastline of India. Okay, so what's the paradox? Suppose that you take a ruler. So if we take a ruler, then our smallest measurement is what? 0.1 centimeter, right? 1 mm. So that means if we have something smaller than that, we cannot measure it properly. But so what we do is that we make an approximation. We try to measure with that much. So suppose that I take a big ruler and try to measure the coastline. We will not do well. I mean, it will give us some approximate reading, but it will not be correct. But what happens if I take a smaller ruler? Then I can do a better approximation. And if I take it even smaller, then I can do much better. But how small should I go? Because the actual coastline has lots of rocks and so on, right? It's not a straight line. So you take smaller ruler, you get bigger length. So this is a never-ending process, right? So how to actually get the right answer? So people were thinking about this. So smaller the ruler, of course, better is the accuracy. But then the idea is to imagine if there is a fractal structure and ask that if you just look at the coastline, maybe it's not one dimensional. Maybe it has slightly higher dimension. Okay, and so of course this was done by this guy called Louis Richardson, and he actually measured coastlines of England and South Africa using yardsticks of different sizes. This was 20th century. This is what crazy researchers do. When there are no means, nothing, they take whatever they have and they just, they're just painstaking that they just do it. Country is huge. To make these measurements, and he, of course, found this, and he had called this coastline paradox. People were trying to explain this, and then it turned out that different countries' coastlines have different dimensions. Okay, so of course, Mandelbrot was the first one after this discovery to give this correct description of this coastline paradox, and he did it using this factor. So this is something called the Van Gogh curve, and so he's a Dutch mathematician. So what you do is that you take this line, you divide it into 3 parts, but you take 4 of those and then you make this shape. And then you go on making this again and again and again. Of course, you can make different shapes as you like, and then you can form your own fractal. And you know how to calculate the dimension, right? The log formula. Okay, so here the dimension is log 4 by log 3, and which is 1.26 or something like that. And actually this matches kind of with Richardson's actual measurements. So he had done this, he had found this pattern, and he had I mean, surmised or conjectured that maybe the dimension should be more than one. And he said that for South Africa, it should be 1.09, seems to have a smoother coast than England, which should be 1.25. And then they were actually explained using fractal structure. Okay, so let's talk about fractals and features of a fractal. And you have seen this already. So it has a fine structure at arbitrarily small scales. It is too irregular to be described very simply, right? You see, even for the Sierpinski triangle, you have to do some procedure infinitely many times. I mean, you don't know how to actually do it. You can't do it in person, but the object exists. It's kind of a weird thing. It's self-similar and it has a simple and recursive definition. So now, what's the point of simple and recursive definition? That you can make computers compute using it. You can feed a very simple definition into a computer and you can ask it to compute. Or you can try to use it to describe many highly irregular real world objects. So, of course, there are many applications. One is in the study of earthquakes, which is seismology. I'll give you one example, which is mountains, modeling surfaces of mountains. So you see, you just start with a simple triangle, but you don't look at it on a plane. You're looking at it in space. Okay. Now you take triangles of smaller size, and then you can actually. So it's actually the triangle roughly of half the size. I mean, exactly of half the size, but it's not kept in a plane. So you can tilt it and so on.
Please stand in the honor of the national song. राष्ट्रीय गीत शुरू हो रहा है। राष्ट्रीय गीतांचा सन्मान आणि
Yes, yes. 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 Yes, but now it's the whole country. I mean, how can you keep a point and take the threads so long and to move it like there will be lots of buildings, houses, fields, everything in the way, right? How to do it? Yes, but at least you can carry I mean, they actually did it with boats. Because you have, I mean, Britain is a country that is enclosed by sea, right? It's like a big island. So they could do it, but like he was crazy enough to do it. But I mean, you see, it's not possible, right, to do it otherwise. You see, these are the days, this is in the 19th century and early 20th century. They didn't have the means. They didn't have mobile phones like Google Maps, things like that, right? So what to do? And when you have up and down terrain, you can't, and people living, life going on, you can't take a thread and just do this. So you have to, this is the way you're going to. But anyway, the point was that, I mean, if you take a country and if you take its coastline, The question was that is it a one-dimensional object? And something doesn't add up. This is what was observed by Richardson. And then this was like, so okay. So coming back to this, what I was saying was that this is using a two-dimensional figure or two-dimensional starting. You start with a simple two-dimensional triangle, but it's kept in a three-dimensional thing. So these are in the second step. There are four triangles. They are exactly half the size of the triangle, but they don't look like that because they may be tilted. They are at an angle. We are looking at them from a distance. And similarly, you can do this, and then for each of these activity, how the geometry works, you can write computer programs to study everything. What kind of things you want to study? Suppose there is a source of water at any point. Where will the water flow? Right? Real world problem. How to build dams, where to build dams, right? Similarly, like what's the magnetic field at various places? Stuff like that. Okay, depending upon what kind of minerals that are there. So on and so forth. So you can write down computer programs to study properties of each of these small scale objects, but not the actual thing is actual mountain is far too irregular. Right. So the coastline thing was a one-dimensional approximation example. I'm giving you a two-dimensional approximation example. Now, depending upon your computing power, you can go as deep as possible and you can write programs. I mean, of course, to do the work, the program will have to run for a long time. And so that has something to do with computing power. And so that's why computer scientists try to develop faster and faster machines with better and better computing power. Okay. So this is an example, and of course, I mean, there are various examples like studying share markets because things that are moving very fast and things that are unpredictable. You want to make models out of it. You want to study them at shorter and shorter time intervals and try to approximate with a fractal. And then that would hopefully give you a better way of, I mean, like modeling it instead of just looking at the figures and trying to look at patterns. And instead, I mean, of course, human minds are not capable of that much computing power. So you want to employ computers to do it. And fractals, because the definition is recursive, everything is recursive, you can easily employ computers to do calculations. Of course, when such a thing happens, of course, it comes into fashion and you can generate several art forms using these kind of things. How simple equations kind of give rise to these art forms, I'll come to it. Of course, when you have such art forms, they land up on t-shirts. Okay, so approximate fractals can be found in nature. And you know, what's the general idea behind fractals? I mean, why does this self-similarity, so the whole point is self-similarity, right? Why should there be self-similarity in nature? So the reason is that unless you are looking at like really microscopic stages, for the things that we can see, we perceive laws of universe that govern large objects, the same laws govern the small objects. So you should kind of, I mean, expect some sort of scalability and self-similarity. And so fractals should be some kind of natural things to, of course, study. Of course, if you go to very small atomic levels, it doesn't work. And then there's a different physics for it. And yeah, so that leads to a whole new subject. That's not my expertise anyway. So anyway, so this is Romanesco properly, which, so these are lots of, I mean, there are lots of things in nature which, I mean, have fractal structures up to 2 or 3 stages or a little bit more. There is sperm that you might have already seen in your school biology, that each leaf is made up of small leaves, which are leaflets, which are copies of the whole. So this is something called Angelica flower head found in Iceland. So if you zoom into at the very end, you see very similar things. The picture is not good enough right now. So these are dendritic copper crystals. I mean, if you see each small branch is similar to the bigger thing, and I mean, in fact, their structure, molecular structure, is actually studied using some sort of fractal approximations. Yeah, it's a similar thing, a fun thing from about Himalayan mountain ranges. view taken from the top, you can see actually there is a sort of fractal structure. There is lightning, and do you know how lightning is studied and analyzed? Properties of lightning. It's actually how to study. If you were to study what lightning causes lots of problems, right? In day-to-day lives, some lives are lost. How do you model lightning and how do you solve it? What you do is, so what is lightning? It's just huge high voltage, right? So what you try to do is that you take a material which will give you good visual feedback, and then you apply high voltage to it. So this is model. So this also has a fractal structure. The way it is that each of the smaller arms is kind of the copy of the whole, but it's just that as it loses more and more power, it dissipates, so you don't see it. And so it's done by high voltage breakdown of acrylic. So you take an acrylic sheet and you give it very high voltage, and you study the patterns that occur. And this is how you model lightnings, and you try to see where there will be biggest damage, where how much voltage will be, and so on and so forth. Okay, and of course, once you know how to do this, you can make it beautiful. These are called Lichtenberg figures. And yeah, there's a whole lot of things you can make. And this is also one of the very beautiful natural crystals formed by frost on cold glass. Okay, so that's now all. And now I want to come back to some very modern stuff. So I'm going to end. This is towards the end of my talk, and I'm going to end by showing you some applications. But before I show you a couple of clips, let me talk a little bit about artificial intelligence. There is a lot of buzz around this word. To be honest, I don't really understand it, but of course it is important. So what you want to do is that you want computational systems to mimic human brain. Okay, so what is human brain? That means you want some sort of decision making ability, right? What does that mean? You want to take a system, you want to abstractify it into mathematics, and you want some way of inputting data and outputting data. Okay, what happens in the middle is something that is decision making, and that's taken care of by so-called neural networks or artificial neural networks, right? How does human brain, what do humans do? We receive something, we hear, we see, we feel, and so on. Our brain processes, and our brain gives instructions to our body parts, and then they do whatever the brain asks them. What happens in between is a completely mysterious phenomenon. How it works, right? We know that it happens through neurons. Okay, so this is just a big net of nerves, and somehow it happens through that. Now, what you want to do is that you want to model such things and see if you can teach computers to mimic that. Okay, so of course, so I mean, fractals, since they have self-similar structures, you want to, create neural nets of smaller and smaller structures. So it's very clear that fractals will probably be useful here, and they will give you slightly better approximations than whatever your other models would try to do. Okay, so this is what I was saying. So there is certain input, there is certain output. Here it's just a two-stage neural network, but what happens in the middle is hidden. Okay, so what so you create a neural network. So how do computer scientists or data scientists, as they are called these days, how do they study this phenomenon? Right? So you have to, what is input, what is output. This is called a data set or data sets. You don't know what is hidden in the middle, right? So you create an abstract system with, so let's say to study, you create a system with just one node in the middle, and then some neurons coming giving you the information and something which is transmitting the information back. So here there is an example with 4, but there are multiple connections. And how are they trained? So you have to train them decision making. You decide what the output is going to be in what format, and you decide what the input is going to be. And so this process is called empirical risk minimization. That means you have to optimize the network's parameters to minimize the difference between predicted output and the actual target values in some given. So there will be some difference in it, and you try to minimize this. And now training depends upon, so the technical term for this is called hyperparameters. That means, so given a neural network, of course it is there. How to initialize it? What will be the first? So the first thing will be some input, and then it starts working, right? So how to initiate it? And at each stage, how, I mean, as it learns more and more, how it will act on it. Okay. So an example of hyperparameters is learning rate. Okay, so you can teach a network, there is a learning rate, which is, I mean, of course, now what's the thing is that you can ask your network to now, of course, this is not all mathematics, there's lots of other areas involved. But once you teach something, how to learn and or how to, and there is a learning rate, how to learn more and more. You know, that's not enough because sometimes we don't have enough computational capacity to see it through, right? Suppose you learn at too small a rate, then you may not learn enough. But suppose you learn at a very high rate, then the knowledge that you acquire is so huge that your output, the computer is not able to handle it. Right? You have gone beyond your computational capacity. Here, the problem is that things like increase at an exponential level, the more the neurons that there are in the middle. Okay, and so the complexity kind of grows more and more as you go through the network. Okay, so there is a very recent result. So of course, what people study is that if you change these hyperparameters, what is the boundary of neural network training? Okay, so there is some optimality, there is an optimal way of training a neural network. Below that, everything is possible, suboptimal. Above that, it's not possible. So they vary this, they plot this. And recently, last year, there's a result which by this mathematician, which shows that the boundary of neural network trainability is a factor. I mean, if there is time during Q&A, I can show you his website where he has put pictures and he has actually studied everything. And which actually shows that, I mean, in fact, in any kind of, so of course, fractals are to be expected in this, in AI and machine learning, because the way it works is self-similar. If the laws governing everything are the same, you have to, you expect scalability and self-similarity. Okay, but I'll now go sometime. So of course, I mean, it's important to understand fractals, but then to understand fractals, you have to see how things scale. You have to understand log, you have to understand exponential, you have to understand how calculus works. You have to see how various things work, and then, you know, this is just the beginning. I mean, people spend lifetimes like doing these kind of things. Now, to go ahead, at the very end, I'm going to show you how fractals came up to use in mobile phones when the mobile phones were first being invented. When was that? 90s. Just before you guys were born. So let's see this.
Tell you fractals are cool. I'm going to tell you fractals are useful, and that's what's important to me.
That's the one.
In the 1990s, a Boston radio astronomer named Nathan Cohen used fractal mathematics to make a technological breakthrough in electronic communication. Cohen had a hobby. He was a ham radio operator, but his landlord had a rule against rigging antennas on the building.
I was at an astronomy conference in Hungary, and Dr. Mandelbrot was giving a talk about the large-scale structure of the universe and reporting how using fractals is a very good way of understanding that kind of structure, which really wowed the entire group of astronomers. He showed several different fractals that I, in my own mind, looked at and said, oh, wouldn't it be funny if you made an antenna out of that shape? I wonder what it would do.
One of the first designs he tried was inspired by one of the 19th century monsters, the snowflake of Helga von Koch.
I thought back to the lecture and said, well, I've got a piece of wire. What happens if I bend it? After I bent the wire, I hooked it up to the cable and my ham radio, and I was quite surprised to see that it worked the first time out of the box. It worked very well. And I discovered that, much of a surprise to me, that I could actually make the antenna much smaller using the fractal design. So it was frankly an interesting way to beat a bad rap with the landlord.
Cohen's experiments soon led him to another discovery. Using a fractal design not only made antennas smaller, but enabled them to receive a much wider range of frequencies.
Using fractals experimentally, I came up with a very wideband antenna. And then I worked backwards and said, why is it working this way? What is it about nature that requires you to use the fractal to get there? The result of that work was a mathematical theorem that showed if you want to get something that works as an antenna over a very wide range of frequencies, you need to have cell similarity. It has to be fractal in its shape to make it work. Now, that was an exact solution. It wasn't like, oh, here's a way of doing it, and there's a lot of other ways of doing it. It turned out mathematically, we were able to demonstrate that was the only technique you could use to get there.
Cohen made his discovery at a time when cell phone companies were facing a problem. They were offering new features to their customers, like Bluetooth, walkie-talkie, and Wi-Fi, but each of them ran on a separate frequency.
You need to be able to use all those different frequencies and have access to them without 10 stubby antennas sticking out at the same time. The alternative option is you can let your cell phone look like a porcupine, but most people don't want to carry around a porcupine.
Today, fractal antennas are used in tens of millions of cell phones and other wireless communication devices all over the world.
We're going to see over the next 10 to 15 to 20 years that you're going to have to use fractals because it's the only way to get a cheaper cost and smaller size for all the complex telecommunication needs we're having.
So this fractal that you see over here. Yeah. So, yeah, so this is similar to this Sierpinski triangle, right? So this is called the Sierpinski cascade. Okay, and the point is that, because of the self-similar structure, you can have different functions on different frequencies, and you can train each smaller part to work on that frequency. And in fact, you get more and more things in your cell phones because you can now produce finer and finer fractals. And so then more and more kind of reports become available to do different things. So that's why your phones are becoming better and better. But of course, this process is slow. Of course, mathematics tells you that if you do this fractal, you get a very nice thing. But then you need advance in material science, materials engineering. You need to be able to make such materials in a cost-efficient way. And as technology moves further and further, you can make more and more finer fractals. You can make them smaller. You can make them more cheaper, efficiently, and that's how it goes ahead. So I'm going to end by showing you this movie, but this movie might be too old for you guys. How many of you have watched Star Wars? This was very kind of taken my English.
Design principles, it completely transformed the magic of special effects.
This is Star Wars Episode 3, where our two heroes have run out into the end of this giant mechanical arm, and the lava splashes down onto the arm. My starting point here is to actually take the three-dimensional model and take essentially a jet and just shoot lava up into the air. This looks kind of boring. It's doing roughly the right thing, but the motion has no kind of visual interest to it. Let's look at what happens here when I add the fractal swirl to it. Where this becomes fractal is we take that same swirl pattern, we shrink it down and reapply it. We take that, we shrink it down again, we reapply it, we shrink it down again, we reapply it. And from here on, it's just a case of layering up more and more and more. I've used the same technique to create these additional lava streams. I then do it again here to get some just red hot embers. Then we take all of those layers and we add them up and we get the final composite image. My hero lava, the front layer, the extra lava, the back layer, the embers, sparks, steam, smoke.
All of these computer animations have always been done like this. You know, you can all you can do is you can see like a strip which is going like this and coming here. Then they just make various versions which are smaller and smaller. They give an angle or like place it slightly off, and then they superimpose everything so that it looks like an actual object. Yeah, and of course, I mean that tells you that how these things are used in the. So now again, there is this problem when I don't know what to do. So I'm now towards the end, so I want to come back to the question that we started with. So what's common to these two things? Okay, so I'm going to let you think about it. I'll just end by, so Mandelbrot has this very nice book called The Fractal Geometry of Nature, and there's a very nice quote out of it. So he says, why is geometry often described as cold and dry? One reason lies in its inability to describe the shape of a cloud, a mountain, a coastline, or a tree. Because clouds are not spheres, mountains are not cones, coastlines are not circles, and bark is not smooth, nor does lightning travel in a straight line. And the nature of fractals is meant to be gradually discovered and not revealed in a flash, and art can be enjoyed for itself. And it's still quite relevant. If you see, basic fractal mathematics is kind of at the cornerstone of modern as well as applied, modern pure as well as applied mathematics. And it definitely has a lot of applications to all. With this, I'll let you think about these two. Thank you.
Before we move towards the end of the session, I would like to ask if anyone here has questions. So please feel free to raise your hand.
I repeat the question because it's giving a lot of feedback. So I think the question was that just like fractals, is there any other modern technology which has its roots in very fundamental mathematics, which was done years ago? So answer is each and every one. And but I'll give you one example. You know, you have I mean, of course, now everybody uses UPI, but still there are people like me who uses debit cards and credit cards. You know what? How do they work? You go to a bank, you put in your card, then you ask how much money you want, and then you have to put a 4-digit PIN, right? And that's supposed to be secure, right? Why does that work? Why is that secure? Just a 4-digit PIN, and it makes everything secure. So the mathematics behind this, you know, the area that contributed to this, the fundamental area, is called number theory. And it's about how to factor numbers into their prime factors, just like you factor 6 as 2 times 3, right? And the okay, how do I put it? So if you, so it goes on the principle that suppose, so the numbers that are easiest to factor, these are the products of 2 prime numbers. Now 2 and 3 are very small primes, but you can take huge primes. You know, there are infinitely many primes. Now, of course, it takes basic mathematics to know that there are infinitely many primes. Then it takes a lot of work to find what are bigger and bigger primes. And then the principle is that you take a prime P and you take another prime Q. You take their product PQ. You can calculate this say using a calculator. This is very easy to factorize. But then if you take P minus 1 times Q minus 1 is really, really hard to factorize. Now the mathematics, the number theory that proves this was done 100 years ago. Okay. Then an algorithm was written. Of course, there's a very, well-known algorithm called public key cryptography or RSA algorithm. This was, so after this mathematics was done in like 1900 to 1920, then the algorithm to do this was developed in the 1974 or something like that. Then to make it usable for banks, when did you start putting your PIN number to an ATM card, ATM machine and started doing it in the 2000s? You see, but you can mathematically prove that. So I mean, of course, it's not, I mean, hack free in the sense that if I cheat and if I see what PIN you are putting, I can hack it. But how does a computer hack it? Right? It does it by trial and error. What do these things do? So you look at how many trials and errors a computer would have to do to hack your password. And you look at the computing power that is available today and see how many, if you employ a computer to hack your credit card or something like that, how many years it would take for that computer to hack it. The best supercomputer that is available today. And then what's the age of the Earth? 4.5 billion years or something. So you make the number of steps required more than that. So then yes, you can employ your computer, it can hack it, but it will take till the end of the Earth. That's good enough for us. Okay. Of course, technology goes ahead, hackers get better, computing speed gets better. But hey, there are infinitely many prime numbers. We can find higher and higher prime numbers, and then we can make this process really bad. That's how it works. That's why it's secure. This is one example. There are tons of them. But this is one I could give off the top of my head. I mean, if you want something closer to this, you can basically try to find out, I mean, surfaces of mountains, how water flows on it, where would there be sources and where would there be sinks? Suppose there is a flood or something, water has to go out, right? Similar problem in topology. Just by looking at the shape, you can study some analysis and you can tell. But all these are different lectures in themselves. Yes.
Sir, I wanted to ask about the topological dimensions. As you mentioned, one of the examples in which the mobile phone antenna,
Yeah.
it was made better
Yeah.
in terms of size and also in terms of efficiency.
Yeah.
So is there any such other example which we use in our day-to-day lives, which has helped scientists and mathematicians to solve?
I mean, all the things that use the same procedure, right? I mean, my laptop, iPads, everything. Everything uses this. I mean, anything that has to receive different frequencies because there are different functions. I mean, employs these kind of things. Yes.
You mentioned the connection between neural networks and fractals.
Yes.
So, can we see future? Today, AI boards like ChatGPT or Cloud work on transformer model. So, how can fractal help them increasing the efficiency of the neural network?
No, fractals don't. I mean, fractals help increasing this thing because fractals are easy to teach. You have to teach a computer to do something, right? You don't do anything. You ask a computer to do something. Fractals are easiest to teach because there will be one recursive definition, one process which has to be iterated. Okay, and that you can tell the computer to do. So it's fractal. And that's there everywhere. Now, how complicated a fractal can become, that is very, these figures, right? These figures are all formed by an iterative procedure. And but what's the iterative procedure that you have to think about it as or ask me. It depends, but fractals are used because it's easy to teach computers how to work with fractals. Because the rules are simple. Any other questions? Yes.
Technical picture.
Okay. None really. Really. It's not even my favorite movie, to be honest. No. I like movies, but not not necessarily Star Wars. I like sci-fi movies a lot. Yes.
Wow, what a ride that was. From known to unknown. Dr. Sawant took us on a journey through the fascinating world of mathematics that many of us has never even known.
From the elegance of Julia and Mandelbrot sets to the mind-bending idea that an n-dimensional object can be torn apart by removing just an n-1 dimension. You didn't just explain dimensions, you made them come alive. Reasons, topological definition turned space into a story, and the documentary on how Mandelbrot hunted hidden dimensions felt like watching math turn into art. You sparked curiosity, lit up our imagination, and made us see how even the most complex structures are built from simple repeating. On behalf of everyone here, thank you for revealing the beauty hidden in the unexplored dimensions and for making them feel a little less mysterious and a lot more magical.
As we come to the end of today's enriching session, I feel incredibly honored to express our collective gratitude on behalf of the entire organizing team. First and foremost, a heartfelt thank you to our chief guest, Dr. Anand Sawant sir, for gracing us with his presence today. Sir, your insights into the unexplored dimensions of mathematics have truly expanded our thinking. The clarity with which you unfolded complex concepts was nothing short of inspiring. We are genuinely thankful for the time you took out for us, especially considering your demanding schedule.
Let me share something special with everyone, which Dr. Sawant has already shared with us. This session was truly worth the wait. Our convener, Dr. Deshmukh sir, has been in constant touch with Dr. Sawant sir for over 2 months. The delay was only because Dr. Anand Sawant sir was in UK delivering expert talks on various advanced topics in math. Oh, sorry, sir. Okay, sir was busy in Germany. We are absolutely thrilled and honored that he accepted our invitation and made time for us today. Thank you so much, sir. A big thank you to the backbone of this event, our visionary convener, Dr. Ambadas Deshmukh, sir. Your unwavering efforts, meticulous planning, and passion for bringing such enriching experiences to us is deeply appreciated. Thank you for everything, sir.
Final thanks to our faculty members present here. Timya ma'am, Leena ma'am, Sushti ma'am, Vicky ma'am, and of course, sir. Final thanks to the volunteers, support staff, PCC members. Your behind the scenes efforts made everything run seamlessly. And to our students, your enthusiastic participation and curious minds added life to this lecture.
Now, before we completely wrap up, let's capture this moment. We kindly request everyone to join us for a quick photo session. First of all, group photo with all attendees. Please stand up on your position.
Other